Hello guys, welcome back to the channel for another Databricks and Spark video. Today we are going to see the basics of resilient distributed datasets, commonly known as RDDs. We will emphasize on the key features of RDDs as it's the fundamental data structure in Spark. Most of us use data frames when writing Spark code. However, data frames under the hood are converted to RDDs, so I think it's important to have a gist of what's going on behind the scenes. I will make a brief introduction about Spark architecture and RDDs, but if you want a detailed explanation or you want to study the theory in depth, I recommend you check out the Databricks and Spark documentation. Here we are going to see a very practical example of how to use an RDD. We are going to use a very popular interview topic when it comes to PySpark, and this is the famous word count example. You know I don't like to waste time, so let's move into the slides. This is the history of Spark APIs. First, we had RDDs, which is an immutable distributed collection of objects. It's immutable, so every time we change the data, we create a new resilient distributed dataset. That also means that we have data consistency, plus we achieve parallel processing. And we can use operations like map, flat map, and filtering. Then we have the data frames, which is a distributed collection of objects, but organized into columns like a relational database. And it provides a high-level API for data processing and a catalyst optimizer for efficiency. And in the end, we have the dataset, which combines the best of both worlds of RDDs and data frames. This is the Spark architecture. We have the driver node, which is the node that we interact with when we write Spark code. It creates Spark context upon startup, which connects to the cluster manager. Now, the cluster manager is responsible for allocating resources. And at the bottom layer, we have the worker nodes that actually run the computations and execute the tasks. So the driver node sends the application code to the worker nodes, and then Spark context sends the task to be executed. As you can see, we have multiple worker nodes, so we can run things in parallel. And once we have the results from the worker nodes, they return the results to the driver, and we can see the results. In a nutshell, this is how it works. Let's see what the definition says about resilient distributed datasets. An RDD is an immutable distributed collection of elements of your data partitioned across nodes in your cluster that can be operated in parallel with a low-level API that offers transformations and actions. There are plenty of key features here that we need to know. It's immutability, which means that once an RDD is created, it cannot be changed. Once we modify the data, a new RDD is being created. Then we have fault tolerance. So since RDDs are immutable, Spark can recover lost or damaged data by rebuilding lost RDD partitions from other intact partitions. To achieve fault tolerance, we replicate the data among different worker nodes in the cluster. Then we have parallelism. We can parallelize an existing collection of data or read data from a distributed file system. So we distribute the data across the nodes in the cluster and in order to achieve parallel processing. Then we have in-memory computation. An RDD can store any media data in the memory so that it provides faster access. The main methods that accommodate this are the cast method and the persist. And last but not least, we have lazy evaluation. This is a very important concept here. That means that the data is not loaded in an RDD until an action is triggered. Let's see the concept of lazy evaluation. So transformations in Spark are lazy, which means that we don't compute the results when a transformation is being called. Instead, we create a chain of transformations maintained through DAG, and then the transformations actually are being executed when an action is triggered, which means when an action is triggered is when we want to produce a result that needs to be sent back to the driver node. There are two basic operations that can be done on RDDs. We have the transformations and the actions. Transformations are operations that accept the existing RDDs as an input and output one or more RDDs. The data in the existing RDD does not change as it is immutable, right? We create a new RDD every time we modify the data. Transformations are like map, flat map, union, filter, reduce by key. There are plenty of other operations that you can check online that are transformations. And then we have the actions. The actions are operations that return a result of RDD computations to the driver node. So after the transformations are done, actions return the result to the Spark driver. Actions can be count, collect, take, etc., etc. I think this diagram here gives you a very good idea of what's happening behind the scenes and the flow with transformations and actions. We have the parent RTD, the initial RTD. We apply a transformation like a map or flat map based on our business logic, and we return a new RDD here, as you can see. And then we call an action when we want to produce a result. That would be like something like save as text file or count, things like that, that actually need to produce a result and send the result back to the driver node. So what are the benefits of having transformations and actions? Is that we reduce computational overhead and we increase speed since we save the tree between the driver and the cluster. And since we don't execute every query, we save time and space. When to use RDDs in general, when the data is unstructured, when we have data sources, media or text streams, or the schema is not important, since we do not impose schema in RDDs. If we want, we have to specify it ourselves. So when the schema is not important, it's better to use RDDs. This is the famous word count example. First, as you can see, we have an RTD input, which is a text file with words. We apply the flat map transformation, which splits the data based on the space between the words and flattens the data. Then we apply the map transformation, which actually adds a new column and assigns the integer 1 next to every word. So we have a list of tuples with the word, and next to the word we have assigned the value of 1. Why did we do that? Because using the reduce by key function, which merges the values of each key based on the function that we provide here, the sum function, then it calculates the total number of occurrences. As you can see, the output is that. We have word 1, and the frequency for word 1 is 4. The frequency for word 2 is 1, and the frequency for word 3 is 4. Let's do that ourselves in Databricks. Okay, so we are in Databricks now. The first thing to know is that we need the Spark context, which is the primary point of entry for Spark capabilities. By default, if we use SC, that stands for Spark context, Spark context has already created by default. Then we have the Spark session, and Spark actually stands for Spark session. There are 3 entry points. That we have Spark context, SQL context, and the Hive context. Now, Spark session that came later on later versions combines the functionality of all those contexts, just for your information. Let's move on to the example. We can read the data from a text file. So this data.txt, which is in our file store, contains a string of words. Actually, it contains a few words. And we can read this file by using .text file, and we point to our Databricks file system, which is a transformation, which is a lazy operation. That's a transformation, right? Now, how can you see your file store? What you have to do, actually, first is to enable this option in the user interface. Click on your account here and click on Admin Settings. Then on Workspace, workspace settings, scroll down, and somewhere you will see the DBFS file browser, and enable this browser here. By default is disabled, so enable that. And if you go back to your workspace and you click on file and you open the DBFS file browser, you will see the file store, and here I have the data.txt, right? And this is how we can actually load this data file using the text file command, which is a transformation as we said. So the data is not being loaded until we call an action. Now an action is collect or take, and this take here is an action and returns the result to the driver node. So let me run the cell and let's see the results. Here we have the results, which is actually a string which has all those words: test 1, test 2, test 3, test 2, test 4, etc., etc. Now test 2, as you can see, we have it 3 times, so frequency is 3 for the word test 2. The rest of the words have frequency of 1. We can create an RDD on the fly from a string. As you can see, it's the same string here, using sc.parallelize, and then we pass the string inside a list. And again, this is a transformation. The data is not being loaded until we trigger an action, which is the collect here. If we run the cell, we will get the same results, right? And the collect actually returns a list. So that's right here. This is not an RDD. This is a resilient distributed data set. When you call collect, it returns a list. So if you try to use the results here for the next transformation, it's going to give you an error because it's not a resilient distributed data set. So this is the RDD that we have now with this data. The next thing we have to do is actually perform the flat map transformation. So it splits the data based on the black between the words, and then flattens the RDD after applying the function, and returns a new RDD. So the new RDD would be called words, and if we called words collect, it's going to give us the results. Here is the list, and as you can see, it flattened the data, right? It split the data and flattened the data. And here we have the next transformation that filters out the data that ends with 1. Now, I just wanted to use the filter operation and the anonymous function, so you can see, a pretty typical filtering operation. So for each row that ends with 1, a row meaning here, so that's the first row, that would be test 1, then the next row would be test 2. So we apply the filtering transformation and we filter out the data that ends with 1. So ends with 1, this is the only word here that ends with 1. So if it equals to false, that means we want the rest of the data. So we are going to filter out this word here, test 1, and we are going, and the rest of the words we are going to remain. So let's run this cell. And as you can see now, we have test 2, test 3, test 2, test 4. We filter out test 1. The next transformation is using, again, the lambda function, the anonymous function, so we don't have to define, it's a very small function. We can define our own function and use it and pass it to the map operation here, but the anonymous function is pretty convenient in our case. So what we want to add on every record here on our RDD is actually add a new column with the value of 1 for each word to create key value pairs, right? And then the output of map transformations always have the same number of records as the input. Let's see what that returns. So we created pairs and we assigned the value of 1 next to each word. And why we did that? Because in our next transformation, which is the reduce by key, which merges the value of each key with the function that we specified, and here we specified the sum function. So based on each key, for example, here we have test2, right? And then we have test2 as well, and we have test2 as well. And the frequency is 1 until this point, but for each key, if we merge the values, that would be 1 here, and 1 here. So the frequency for test2 word is 3. But for the rest, because they are distinct, we have distinct keys, would remain 1. Let's perform this reduce by key transformation and see what we get. And as you can see here, everything, every word has the frequency of 1 except for the word test2, which has frequency 3. Perfect, right? And this is how you can get the word count in a resilient distributed dataset. Now, for example, if you want to sort by key and get only the first element, so let's say we want only the word with the highest frequency. That would be actually the tuple with the highest frequency. That will be test2, and which has frequency 3. How can we do that? Again, we need to apply the map transformation and the anonymous function, and for each record, we switch the position of the key and the value. So the value becomes the first, goes into the first position, and the key goes into the second position. Why is that? Because the sort by key actually gets the first column and sorts by the key, and that's why we move that. So the 3 goes here, and test2, the string, goes here. So then we can sort by key, which would be the value in our case, the frequency, and we get the first result. So we sort by, and then we get the first result. And here, as you can see, we can apply a transformation, which is the map transformation, sort by key, which is another transformation. So the data is not being loaded until an action is triggered. And here, dot first, this is an action. So this will return the results to the driver node. If we run this, you will see the outcome would be the tuple with the highest frequency. We can use another action, which is save as text file. Let's result test, for example. But here, if I run this, because the outcome now is a tuple, it's going to give us an error. So let's run this. You will see an error. Tuple has no attribute save as text file. Let's rerun, remove the action here, and let's, now we have an RDD, and let's run this save as text file action. And if we go into our dbfs file browser, you will see the result test.txt. A few other things you would like to know is the repartition method that actually can increase or decrease the number of partitions. Remember, a resilient distributed dataset distributes the data across multiple partitions, so it can process the data in parallel and be more efficient. So the repartition method creates new partitions and tries to evenly distribute the data in those new partitions, but it also performs a full shuffle, so that means it's an expensive operation. Let's print the current number of partitions and see how the data is distributed across those partitions. So we have 4 partitions, and in one partition we have test1, then we have in another partition test4, in the third partition test5 and test7, and in the last one, in the fourth partition, we have test2 and test6. Now let's repartition the data and create 3 new partitions and distribute the data across those partitions. If we repartition the data, as you can see now, we have 3 partitions. Let's see how they are distributed. As you can see now, we have test 3, test 2, and test 6 in one partition, test 4 in another one, and test 5 and test 7 in another one. So we decrease the number of partitions by 1. But we can use, for this operation, we can use coalesce, which can only decrease the number of partitions and not also increase like the repartition method. But coalesce uses the existing partitions to minimize data shuffling, so it's not as expensive as repartition, so it's more efficient in terms of performance. Now let's run the coalesce method. Actually, reducing to one partition is not very clever, so let's reduce it to decrease the number of partitions by 1. So in total we would have only 2 partitions in the end, and let's see what we get. So we have 2 partitions now with test 3, test 2, and test 6 for the first partition, and test 4 and test 5, test 7 for the second partition. The takeaway here is when you want to increase partitions, use the repartition method. When you want to decrease the number of partitions, usually it's better to use coalesce as it's more efficient. Now, we have another thing I would like to mention is caching and persistence, which are optimization techniques for iterative Spark computation. So let's say we don't want to recompute the same values and we want to start from the latest result, so we can save the immediate results in memory. We can use cache or to keep the data in memory, or we can use persist, which you define actually the storage level. I think there are 4 storage levels if you run this operation. But for more information, just check the documentation about persist. This is it for today, guys. I hope you enjoyed the video and it was a clear introduction to resilient distributed datasets. Of course, for more detailed explanation, it's better to check out the Spark documentation. I believe the word count example comes in handy as it demonstrates both transformations and actions. It's also useful because it's a common interview topic. If you like the video, please click the like button, leave a comment and subscribe to the channel, and I will see you in the next one. Thank you.